refers to the idea that the distribution of a variable is constant as plotted across an xy axis. For example, here are two distributions. The first in the upper left-hand corner with constant variance, where all the observations lie almost exactly the same distance away from the regression line. The second distribution in the lower right-hand corner has non-constant variance. Notice how the observations start out close to the regression line and then extend away from the line in both directions as values of x and y increase across the progression. The line for both of these regressions will be the same, which causes a problem because regression analysis does a much better job of predicting values of the dependent variables up here for the distribution with constant variance than down here with non-constant variance. That's why the assumption of constant variance is crucial for regression analysis. The mean values for both regressions in both cases are accurate, but it's only useful to use the regression to create estimates for the first distribution because of the constant variance. For the second one, estimates will be close to the actual values for the first part of the distribution until about here, and then get increasingly poor as the distribution progresses. The solution to this problem is found by knowing one's data and plotting it on a scatter plot, usually using SPSS, to see whether the variation is more or less constant. This brings me to the second assumption of this module, that of linearity. Regression analysis allows us to draw the straight line that passes closest to all of the observations in a distribution. This is a powerful tool, but another one of its drawbacks is the straightness of the line that it draws. There are many relationships between phenomena that do not follow a straight line, but instead change the rate at which they increase or decrease with one another. For example, a car accelerates to a top speed, and the graph of its velocity over time looks like this. Regression analysis will do a terrible job creating estimates of this line because the distribution is curvilinear, but regression will draw a straight line based on the average values. It'll look something like this. Regression can still be useful if we have data over a long enough time frame and the car does not accelerate much, but if the car is increasing in speed, decreasing in speed, or we're looking at a shorter time frame like this, the line won't help us much because the car accelerates faster than the regression line gives it credit for, and then it reaches a top speed and plateaus, whereas regression analysis will send it on into infinity. In this case, the data in this distribution is not well suited to regression analysis using the linear tools we'll learn in this class. The solution is to use nonlinear models you'll learn about in an advanced statistics class. But for this class, the point is to be mindful and understand something about the data and the relationships you are trying to model. You can think about this critically from the perspective of whether you believe the relationships for your data are likely to be linear or nonlinear. In this sense, you might think of it in terms of the likelihood that as y increases or decreases, will it be the same amount for each increase or decrease in x? Why or why not? For this example, as time increases from 0 to 1 second, the car's velocity increases at a certain rate. From 2 to 3 seconds, the car's velocity changes and increases at a faster rate. But from 5 to 7 seconds, it's likely to start slowing down even though it might be accelerating. The rate of increase might be slower. In this case, it's clearly not a linear relationship in terms of a straight line. Keep this in mind for your own projects. but this is an argument that you will be able to make with your data, not necessarily show based on SPSS analysis at this stage.